Hello to everyone. Welcome to the course on numerical linear algebra and application. Today we are going to have the 13th module, 61st lecture. We would review some things which already we have done it in the beginning. So as a matter of fact, it's a recalling and recapitulation lecture. Look at this. There would be in this lecture, we would be covering review of basic concepts. Then we would be doing vectors, inner products. What are the definitions of vectors? How the inner product would be created. And there is a what you call orthogonality. Then we will go for basis, matrices, determinants. Then we will go for range, null space, rank of a matrix. Then inverse of a matrix, some special matrices, unitary and orthogonal matrices. Then we will have symmetric, Hermitian matrices, eigenvalue decomposition of symmetric matrix, Heisenberg matrices, vectors and matrix norms, the Frobenius norm, norms and inverses, then norm invariants properties, and some new examples which we would like to cover in the today lecture. See, in the review of basic concepts, we know what is the linear algebra. Basically, linear algebra is which preserves the linearity, linear transformation. That is, if T is the transformation from U to V, then T of U plus, that is some alpha times, alpha is a scalar, beta is another scalar, alpha times of Tu plus T times of beta U will be equivalent to alpha times of T of U plus beta times of T of V. That means basically which will preserve the linearity. That is what is called linear algebra. With this numerically, this linear algebra, rather the elements of the matrices, that is horizontal rows and vertical columns, horizontal rows and vertical columns. These horizontal rows and vertical columns will form a matrix. And these entries of this matrix are floating point numbers. Floating point numbers. That is, for example, I will have 0.001, 0.10123, 2.424, 0.526, 1.324, 0.0012, like this, the floating point numbers. So they are all fractionals. That is what the basic. So that means You want to include numerical values, numerical plus preserving the linearity. That's how it has become numerical linear algebra. And we are associating with applications. So that's why it is called numerical linear algebra with applications. With applications. That's the basic idea of the numerical linear algebra and applications. See, look at this. Initially, there are various types of matrices. We have seen the main diagonal entry, which is the leading elements. So, this is a diagonal element, which we call it as a diagonal matrix. And you will have tridiagonal matrix. Tridiagonal matrix. Then we will have bidiagonal matrix. Bidiagonal matrix. Then you will have Heisenberg matrix. Like this, Heisenberg matrix. Heisenberg matrix, right? Then you will have symmetric matrix. Skew symmetric matrix. Skew symmetric matrix. Hermitian matrix. There are many more matrices like this. Well, so when it comes to the vectors, we know it's a ordered set of numbers, you know very well. Ordered set of numbers. That is what we call it as a vectors. Then we will have a row vector. Then we will have a column vector. And we have different properties. We have different properties. That is, if u and v are two vectors, which we call it as additional property. So that is component wise, u1 v1, u2 v2, u3 plus v3, so on and so forth. Similarly, we see the scalar. We write it as c times of u, that is equal to cu1, cu2, cun transpose. So then you know very well the inner product. The inner product. So inner product is, you know, there is a u times of u transpose, which we will write it as u1 v1 plus u2 v2 plus etc. un v of n. That is the inner product. then the length of the vector is we'll denote it as v1 square, v2 square, etc. under square root, which we call it as length of the vector. So also we say that linear independence. So if the vectors, let us say m1, m2, mn, they are all in the set R of n. Right? These are the vectors in the R of n. And there are scalars C1, C2, C3, C of n, scalars. Then the linear combination m1 C1, m2 C2, mn Cn will be equal to 0, implies all C1 is 0, C2 is 0, C3 is 0, all Cn is equal to 0. Then we call it as linear independent. So the vectors are said to be linear independent vectors. Suppose if alpha not equal to 0, a scalar, such that m1 c1, m2 c2, alpha times of ck plus etc. plus ck plus 1 etc. is 0, and alpha is not equal to 0, and ck is not equal to 0. Ck could be 0 or not equal to 0. So if there exists at least one non-zero scalar, such that the linear combination happens to be 0, then the vectors are linearly dependent. Then the vectors are linearly dependent. So it is very clear from this concept how the vectors are linearly independent, how the vectors are linearly dependent. Then also we will have what we call the matrix properties. All of you knowing very well matrix properties. Matrix properties. Sum of two matrices then complex conjugate of matrices, square matrices, triangular matrices, and so on and so forth. Also we can have the block matrices, very important, which we have already seen in several places. Block matrices. So block matrices also plays a vital role. That is you will have a blocks. So this is the one block, this is another 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 block, this is the another block. They're called block matrices. Block matrices. So block matrices also, the sum of two block matrices also follow addition property. Similarly, we will have a determinant of a matrix. That is, determinant is all of you know very well. So it is the most important property. For example, if we have this matrix, then what we do is the 3 by 3 matrix. So 3 by 3 matrix we reduced into 2 by 2, that is 1 times of determinant of 5, 6, 8, 1, and it is minus 2 times of determinant of 4, 6, 7, 1, plus 3 times of determinant of 4, 5, 7, 8. So this will become 5 minus 48 minus 2 times of 4 minus 42 plus 3 times of 32 minus 35. So if you simplify all these things, it turns out to be 0. So determinant of 3 by 3 order is 0, and 2 by 2 order at least one is not 0. So rank turns out to be, from this rank of this matrix turns out to be less than 3, that is 2. It's one of the very, very important property which we do it in the numerical linear algebra. Similarly, we will have what we call the properties which we also do have orthogonal property. Orthogonal property is also one of the important property which we could see it. Two vectors, for example, if we take two vectors u and v, are the two vectors. So that is cos theta is equal to u transpose v upon norm of u times of norm of v. Right? This is what we call it as a orthogonal property of two vectors. So we say that u and v are orthogonal. U and v are orthogonal if theta happens to be 90 degrees. That is, essentially U transpose V happens to be 0. Many books and all they use as U transpose perpendicular to V. That means the angle associated with these two vectors is 0. We call it as a orthogonal vectors. Similarly, if you have two subspaces S1, S2, they are all in R of n and they are said to be orthogonal. For every S1 belongs to S1, S2 belongs to S1. So that is, so we denoted by S1 is orthogonal to S2. That means two spaces are orthogonal to each other. And as we have seen, there is a what you call the dimension of the space, which we call it as the dimension of the space. So that is which we call it as the UI transpose U of j will be equivalent to 0 for I not equal to j. And U of I transpose U of I is equal to 1. So linear combination of these vectors, then we call it as a orthogonal property of these vectors. That means the inner product, when you talk in terms of inner product, later on we will talk it about Ui times of Vi, inner product. If it happens to be 0, then we will say that Ui is perpendicular to V of j, or I is equal to j, whatever. So after having the determinants, we will have a very specialized matrices when you have it. For example, the determinant of a block matrix. So we will have A is equal to, let's say, A11, A12, 0, A22. So then we are writing determinant of A will be equivalent to determinant of A11 times of determinant of A22. That means product of these two things, leading diagonals. So which we call it as a determinant of the matrices. Similarly, how do you define this, what we call the, how do you define the, what we call the characteristic polynomial? Characteristic polynomial. So in the characteristic polynomial, we write let A be a n by n matrix. Let A be a n by n matrix. So we write it as Pn of lambda, that is equal to determinant of lambda I minus A. So this is called the characteristic polynomial. Characteristic polynomial is called the characteristic polynomial. So then in general the zeros of the characteristic polynomial are called eigenvalues. So what are the different properties you have eigenvalues? The properties of eigenvalues are A and A transpose have same eigenvalues. So a matrix A is non-singular A becomes non-singular if and only if all its eigenvalues are non-zero. Third point is the eigenvectors corresponding to the distinct eigenvalues. Distinct eigenvalues are linearly dependent. So these are some of the basic properties of the matrices. Then you do have what we call the very important properties. The what do you call this? How do you find out the determinants? So there are some properties. For example, if you have the what do you call this diagonal matrix or tridiagonal matrix, let's say that. So when you multiply these cofactors, so many cofactors happens to be 0. Many cofactors happens to be 0. So therefore, you can able to find out easily the determinant of this matrix. Now the next thing is range and null space rank of a matrix. So for every matrix, M over n, so we write it as the range space R of A is nothing but the set of values of B which belongs to R of M such that B is equal to A of X for some X belongs to R of N. The null space of A is equal to, that is, X belongs to R of N such that Ax is equal to 0. So null space is which will map to a 0 space, and range space is B is equal to Ax or Ax is equal to B. So S perpendicular we can define it as set of values of Y belongs to R of M such that Y transpose X is equal to 0 for all X belongs to S. So we can write orthogonal complement as so n of A is equal to, you can have range of A transpose perpendicular, and this is the first property. Second property is range of A perpendicular is n of A transpose. So based on that, we can find out what you call the rank of a matrix. So that is, you will have a vector that is M over N matrix. Then the subspace spanned by the row vectors of A is what we call the subspace spanned by row vectors of A is called row space of A, which we call it as row space of A. Similarly, the subspace spanned by the columns of A is column space of A. The column space of A. So that means, so essentially the rank of a matrix is the dimension of the column space of A. The column space of A. So which we write it as rank of A. Rank of A is nothing but the column space of A. So in this fashion, a square matrix that is A belongs to R of n over n is called non-singular if rank of A is equal to n, otherwise it is singular. Otherwise it is a singular matrix. So if you have the matrix A 1, 2, 3, 4, 5, 6. So rank of the matrix is, that is 3 by 3 is not possible. So there should be at least one non-zero of 2 by 2, that is 4 minus 6, minus 2 not equal to 0. So I can write it as rank of A is equal to 2 in this case. Similarly, if you look at into another example, A is equal to, let's say, 1, 2, 2, 4, 0, 0. Look at this, 3 by 3 is not possible. And 2 by 2, there is at least one 2 by 2 matrix whose determinant is free from 0. So it does not. Right? And there is at least one over one element whose determinant is free from 0. So rank of A is obviously equal to 1. So rank of A is equal to 1. So therefore nullity of A is also equal to 1. Rank of A is equal to 1. So nullity of A is also equal to 1. In the previous case, if you look at here, in the previous case, rank of A is equal to 2. So what is the nullity? Nullity of A is equal to 0. Right? So if rank of A is equal to 2, nullity of A is equal to 0 over here. Right? So basically the idea is the nullity of A is range of A of transpose. They are all orthogonal. And rank of A is the range space of A is orthogonal. So that means the range of A is nothing but the set of all values of B such that B is equal to Ax, where nullity is mapped to the 0. So therefore, the rank of matrix is the dimension of the column space of A. Dimension of the column space of A. It is denoted by rank of A. Suppose if there is a matrix A n by n is said to be full column rank if its columns are linearly independent. So a matrix A is said to have a full rank if it has either full row rank or full column rank. So if it doesn't have full rank, we call it as a deficient matrix. After some time, probably you will be hearing a theorem called Cayley-Hamilton theorem. What it says is rank of a matrix plus nullity of a matrix A is equal to dimension of the vector space, dimension of A. Also, we can see some of the properties of these ranks, that is, rank of A is equal to rank of A transpose. Then rank of A plus rank nullity of A, null of A is equal to small n. There are properties, very basic properties. Similarly, we can also have the inverse of a matrix. How inverse of a matrix can be defined? Let's say A is a matrix of n over n. So we write it as AB is equal to BA is equal to I. So inverse of A inverse is unique. So there cannot be any two inverses. The inverse is unique. So what this theorem says is, if A is a matrix of R of n over n, has an inverse as an inverse, it is called non-singular. It is called non-singular. Otherwise, it is singular. So a non-singular matrix is invertible. So what is the characterization of a non-singular matrix? Characterization of a non-singular matrix. The characterization of a non-singular matrix is determinant of A is not equal to 0. A has linearly independent rows and columns. Linearly independent rows and columns. Third point is n of A is equal to 0. The fourth point is The eigenvalues of A are all non-zeros. The eigenvalues of A are all non-zeros. The fifth point is rank of A is equal to rank of A transpose. That is, rank of A is equal to rank of A transpose, which is equal to N. So when you talk about the similar matrices, two similar matrices have same eigenvalues. Two similar matrices have same eigenvalues. So that means if the matrices are two similar matrices, they have the eigenvalues. So A and B are similar matrices if there exists a matrix X such that X inverse Ax is equal to B. Then we call it as matrices A and B are similar matrices. So let us look at into the some special matrices, unitary and orthogonal transformations. Well, look at this, which you have seen the some black diagonal matrices in the last lecture, and also some very specialized matrices. Look at over here, you will have a matrix like this. This is the matrix, and all are zeros. These are all non-zeros, like this. This is the lower triangular matrix, and you will have another matrix which is zeros, upper triangular matrix. And obviously you have a what you call, this is diagonal matrix, diagonal matrix. So apart from these, you also do have, apart from this, you also do have matrices like unitary matrix. Unitary matrix. We define in the following fashion: a square complex matrix U is unitary if U transpose U will be equivalent to U times of U transpose, that will be equivalent to I. So U star is nothing but U bar transpose, where U bar is the complex conjugate, is the complex conjugate of capital U. So if U is real, then U is orthogonal. U is orthogonal if U transpose U will be equivalent to U times of U transpose will be equivalent to I. So you will have theorems. If you look at one, the inverse of an orthogonal matrix orthogonal matrix O is just its transpose. That is, O inverse is equal to O transpose. Second one is the product of two orthogonal matrices. Matrices is an orthogonal matrix. Then you will have a symmetric matrices, as you know very well. Then you will have a symmetric matrix. Then you will have a Hermitian matrix. Symmetry matrix, Hermitian matrix. Then also we have what we call what we call Hermitian matrices. So also there are some properties, the eigenvalues of a triangular matrix. Or its diagonal entries or its diagonal entries. Well, the symmetric and Hermitian matrices. So we call it as a square matrix. A square matrix, A is Hermitian if A star is equal to A, which we call it as Hermitian. So a square matrix is symmetric, a square matrix is symmetric if A transpose is equal to A. If A is real, then A is real symmetric. A is real symmetric. If A is real, then A is real symmetric. So normal convention is real symmetric matrices are considered as symmetric matrices. Then you have a eigenvalue decomposition of symmetric matrices. So it can be done in the following fashion. Let A be a complex Hermitian matrix. Let A be a complex Hermitian matrix. Then there exists a unitary matrix U such that then there exists a unitary matrix U such that U star AU will be equivalent to diagonal of lambda 1, lambda 2, lambda n, where lambda 1, lambda 2, lambda n are the eigenvalues of A. Are the eigenvalues of A. And the another property is the eigenvectors of a complex Hermitian matrix. The eigenvectors of a complex Hermitian matrix. Complex Hermitian matrix can be chosen to be unitary. Can be chosen to be unitary matrix. So when you write this matrix, let A be a real symmetric matrix. Let A be a real symmetric matrix. Then there exists an orthogonal matrix O such that O transpose AO is equal to D, where D is diagonal of lambda 1, lambda 2, lambda n. Then you do have a Heisenberg matrices. They are called almost triangular matrices. So you have a matrix like this, zeros, you have a matrix like this, and you have another matrix like this. You have another matrix like this. So this is what is called the lower Heisenberg. And this is what is called upper Heisenberg. Upper Heisenberg. And this is called tridiagonal. This is called tridiagonal matrix. So, an upper Heisenberg matrix. An upper Heisenberg matrix A is equal to Aij is unreduced if Ai minus 1 is not equal to 0 for I is equal to 2, 3 up to n. Similarly, a lower Heisenberg matrix A is equal to Aij is unreduced if Ai I plus 1 not equal to 0 for I is equal to 1, 2, etc. n minus 1. So you will have A is equal to 1, 2, 0, let's say 2, 3, 4, 1, 1, 1 is an unreduced lower Heisenberg matrix. Is an unreduced lower Heisenberg matrix. And similarly, if you write A is equal to this matrix 1, 1, 1, 1, 1, 1, 0, 2, 3, this is unreduced upper Heisenberg matrix. Unreduced upper Heisenberg matrix. Upper Heisenberg matrix. Then vector and matrix norms. So that is norm of x is greater than or equal to 0 for every non-zero. That is x dot norm of x. So that is equal to 0 if and only if x is a 0 vector. X is the 0 vector. This norm of alpha x is equal to mod of alpha into norm of x for all x belongs to R of n. Alpha is a scalar. Third one is norm of x plus y is less than or equal to norm x plus norm of y for all x, y in the R of n. This is what is known as triangular inequality. This is known as triangular inequality. So you can also write it as norm of x of 1 is equal to, that is x1 plus x2 xn, some norm or one norm. And similarly norm of x of 2, that is equal to x1 square, x2 square, xn square under square root. So this is what is called Euclidean norm. Euclidean norm. And third one is what is called, so this is called maximum of I mod of xi. It is called the infinity norm. It's called infinity norm. So in general, if p is a real number greater than or equal to 1, then p norm, or which we call it as Holder norm. Holder norm, that is norm of p, which will be equivalent to x1 power p like this, x1 power p raised to the power 1 over 2. This is what is called the vector norm. Similarly, you can take some examples over here. For example, I have a let x is equal to, let's say, 1, 1 minus 2. Then what happens? Then norm of x1 will be equivalent to 4, and the norm of x2 will be equivalent to, that is, if you calculate 1 square, 2 square, that is equal to square root of 6. And norm of x of infinity norm is 2. So that means x transpose y is less than or equal to norm of x, sorry, p norm of y of q. So the relation between these two things is 1 over p plus 1 over q is 1. So a special case of Holder's inequality, which also we call it as the what do you call the special case of this inequality is also called the Frobenius norm. So which we also call it as the Frobenius norm, which we will do it at a later time. But this vector norm, we can write it as the what do you call this the vector norms. So matrix norm, and I see that the analogous of the matrices is there is a quantification. So quantification of the matrices is by using the norm. So that is, you will have the norm of A, that is greater than or equal to 0. Norm of A is equal to 0 if A is equal to 0. Then norm of alpha times of A, that is equal to mod alpha into norm of A. Then norm of A plus B will be equivalent less than or equal to norm of A plus norm of B. So essentially what I mean to say is, that is A of 1 will be equivalent to maximum of 1 less than or equal to j less than or equal to n. That is summation I is equal to 1 to n m mod of aij. Then norm of A infinity is maximum of 1 less than or equal to I less than or equal to m mod of aij, maximum row sum. So that means A is equal to, you will have 1 minus 2, 3, 4, minus 5, 6. So that is A of 1 is equal to 12, and the norm of A of infinity is 11. So that's how we do compute the vector norms. Look at this second norm, which we call it as Frobenius norm, which is very, very important. That is norm of A of f, that will be equivalent to summation j is equal to 1 to n, summation I is equal to 1 to n, mod of aij whole square raised to power 1 over 2. For example, if you look at this example, A is equal to, let's say, you will have 1, 2, 3, 4. Then norm of A of F. Frobenius norm is, that is 1 square, 2 square, 3 square, 4 square under square root. So 1 plus 4 plus 9 plus 16, so that is equal to square root of 30. That is called Frobenius norm. So very important property of this Frobenius norm is that how actually they would be able to look at these matrices. For instance, alpha times of, that is norm of A, so which can be written as less than or equal to norm of A infinity, that is mu norm, that is beta times of norm of A. And similarly, there are other applications equivalent to that of the norm, how you could able to find out the norm and its inverses. For example, norm of A infinity, so you can write it as maximum of x not equal to 0, that is norm of x infinity upon norm of x of infinity. So also A times of x of infinity is less than or equal to norm of ax of 2, and norm of x of 2 is less than or equal to root n times of norm of x of infinity. So these kind of examples one can do it. So I will stop over here. Thank you very much for listening to my lecture. So in the next lecture we will do some more examples in pertaining to what we call the norm and inverses. Okay, thank you very much.